Well, hello, welcome to week 7. In this week, we're going to be covering chapter 14, where the big broad topic is investment. So, what we're going to be doing today is to think about um, how investment decisions are made. So, in order to think about that, we're going to first have to remind ourselves of what investment is. And then our objective with this is ultimately to be deriving a downward sloping investment demand curve and to use that ultimately in a couple of places. One is in the characterization of the loanable funds market that we'll do in this discussion of chapter 14, and then the second place in which we'll use this in a big way is in the construction of the business cycle model that we'll develop beginning in chapter 18. So for today, what we're going to do is to, again, define what we mean by investment, review some definitions, and then think about how an economic agent like a firm would go about making a decision as to whether to undertake investments. So for me, when I'm thinking about this, that sounds like even more than is typical econobabble. And so I think about, does a firm want to buy a machine? Yes or no? The thing that is fascinating to me about investment as a topic and finance as well as a subdiscipline in economics is that you have this intertemporal aspect to the decision making problem. So we will see in our example today, and this is kind of emblematic of any kind of investment decision, the costs are borne upfront or mostly upfront, and the benefits from the activity are going to accrue over a period of time going into the future. So we'll think about what that means in terms of how we go about decision making, and then we will, as I said, use that a little bit later as we go through the semester. So if you recall, in the last set of notes, we talked about consumption, a related idea in the sense that consumption, investment, government expenditures, and net exports are the spending categories when we're thinking about defining GDP on an expenditures basis. You'll recall that we talked about consumption as being relatively large, about 68% of overall gross domestic product. And you can see, of course, that investment is a fairly significant, is a decidedly smaller portion of real gross domestic product. But the interesting aspect of it from a business cycle point of view is that it is extremely volatile. And so what I have mapped here, pulled down from Fred, you can see if you follow the hyperlink that's up there on the upper left, is a graph that shows in blue real gross domestic product, in green personal consumption expenditures, and in red gross private domestic investment. So just as a little side note, the definition, the way in which real personal consumption expenditures is made, the way in which it is measured changed in the early 2000s, and so that's why this data series only goes back to about 2001 for consumption expenditures. But you can see the green and the blue lines track each other very closely. So while consumption is a huge part of gross domestic product and certainly important in that respect, a lot of the volatility that we see in gross domestic product is induced by, or certainly correlated with, the volatility that we see in investment. What I want to do is remind ourselves of what we mean by gross private domestic investment. So notationally, and what we're going to be doing later, we're going to use capital I here to denote gross private domestic investment. And again, investment is probably, of all of the spending categories in gross domestic product, the trickiest one for us to keep straight. And that's because we are constantly bombarded by sort of the colloquial or day-to-day use of the word investment. And as is the case in any discipline, there are words that mean very specific things in disciplines, and economics is clearly no exception to that. So when we're talking about investment, in economics, we are talking about spending on new capital assets. So, capital, again, we can think about this, I think about it as especially, it's not limited strictly to physical assets, but we can think about physical capital. And the easiest thing to think about, again, I think, in this context is just a machine. So physical capital or capital assets are goods that are available to produce more goods and services in the future. And so when we're talking about investment, we're talking about spending on these capital assets. And it's important because the more investment we do, other things equal, the higher will be the economy's productive capacity in future years. You will recall, I hope, that when we talked about gross private domestic investment, we said it is divided into three pieces. Business investment, this is sometimes called business fixed investment. And I think also when we did this in the notes, I called this non-residential investment. Inventory investment and housing investment, or when we talk about housing investment, this is sometimes referred to as residential investment. So this is the part of spending by households that is not included in personal consumption expenditures, because again, we think about a house as being exceptionally long-lived and therefore more like other kinds of physical capital in that it yields a stream of returns for very, very long time periods. When we think about investment and we say it adds to the capital stock, what we mean by that is that from a notational point of view, we will later on define the capital stock with a letter K. So, in other words, if we were going to ask ourselves what is the value of all the machines and buildings and houses and other kinds of things that fall into the category of capital that we have at a point in time, it would be the amount of physical capital that we had previously, plus any investment that happens in that time period. And then some of the capital stock gets used up. So things deteriorate or their usefulness erodes, and so that's how we think about depreciation. So the evolution of the capital stock from one year to the next can be described by this equation. And if we have a chance to get into the material that's in Chapter 10 at the end of the semester, we'll play with this equation a little bit more. It is important to note that countries that have more capital per worker have more output per worker. So output per worker, output is gross domestic product. So we think about this as output per worker. This is similar to, so again, we have GDP we can think of as a measure of output, but we can also think about it as a measure of income. So income per worker. And this is at least correlated with the number of workers in an economy is correlated with the size of the population. So income per person, and this is per person or per capita. We said we could think of this as a, not the, but a measure of our standards of living. So from a practical point of view, one reason why we focus on investment expenditures in the macroeconomy, in addition to the reasons that we've already spoken of, is that more investment, other things equal, will translate into a higher capital stock, which itself, other things equal, can translate into can translate, not will, into improvements in our standards of living. So this graph was in the textbook. It's just an illustration of the relationship between countries' capital per worker and output per worker. And again, you can see this positive relationship that's exhibited here. In order to think about analyzing investment opportunities, and by that, again, what we mean is this yes/no decision of whether we say buy a machine if we're a firm. The other example that got play in the textbook and I think is profound and important is you are undertaking investment in yourself. So how do you analyze this decision of should I go to college at all or should I go to school for another year? These are basically investment decisions in the same spirit as what we're talking about here. So it's a more colloquial use of the word investment compared to how we think about it again in a macroeconomic context. But nonetheless, the other thing that I think is nifty about this particular set of notes is that there's a skill set here that you can apply broadly in your life going forward. And heaven knows, a lot of these notes I try to have usefulness, but maybe it's not as broad as this one is. So, in terms of analyzing investment decisions, there are two main tools that we're going to think about. One is the notion of compounding, and the other is discounting. And these are just flip sides of the same thing. So what do we mean by compounding? So when we're thinking about compounding or when we're discussing compounding, we're again thinking about interest rates. So here's our kind of second look at interest rates, and we'll have a lot more to say about interest rates as we go forward for the rest of the semester. But we can think about an interest rate as describing how an amount of money grows from one period to another. So here's my very simple example. Suppose you save $1,000 in a checking account or savings account that pays you 6% interest. In 1 year from now, so you make your deposit, in 1 year from now, you would get your $1,000 back plus the interest that accumulated on that $1,000. So that would be 1,000 then times 1.06 or 1,000 times 1,000 times 1 plus 0.06 or 1,000 times 1.06. And so what is this 1,000? The 1,000 we can think of as the principal or the value today, today's value. And what you're going to get in a year is the future value, of course. Now, suppose you saved this amount again for another year, so you accumulated interest on it in the first year. Then this amount is what you would be starting with. That would be what you're starting with at the outset of year two. Again, you earn interest on that, and so if we wanted to think about what your amount of money that you would have after 2 years, the future value in 2 years is the value that you have today, so way back today, times 1 plus the interest rate squared. So in other words, this would be, in our example, $1,000 times, as I have over here, 1.06 squared. So the phenomenon of discounting is just flipping compounding on its head. So if we were going to think about discounting, we're rather than, as we did here, thinking about how does an amount of money grow from one period to another, with discounting, what we're doing is we're saying, suppose I have a promise of receiving a certain amount of money in the future, say T periods ahead. What's it worth to me today? and that what it's worth to me today is the today's value or the present value. And so what we do is we take this relationship that we had on the previous slide, which I've reproduced here. So the future value of the amount of money that you're going to get, say, t periods into the future, is of course the amount that you start with today times 1 plus the interest rate raised to the t power, where t is the number of years into the future. So the present value is just flipping this relationship around. So the present value of an amount to be received in the future is that future value divided by 1 plus the interest rate raised again to the power of t. So we have two observations that we can make about this present value concept. And one of these is for a given interest rate, the farther into the future an amount is to be received, the smaller is its present value. So what I want to do is think about why that might be. So first of all, what I want to do is go through some numbers. So suppose that the interest rate is, let's say, 2%. And if you are promised say $100 in a year, we could ask, what is that worth? Well, it's not worth $100. It's in fact worth less than that, because if you had $100 today, you could have put it in the bank and it would have grown by our previous discussion of compounding to become $102. So you would have gotten the interest in a year from now. So the promise to get $100 a year from now is not worth $100. It has to be worth less than that because of the interest income that you've given up. And so, in fact, we could think about what that present value is. The present value is going to be the amount that you're promised in the future divided by 1 plus the interest rate raised to the number of periods into the future that you're going to receive this. So trivially, that's a 1. And what this would turn out to be, if I did my math correctly, is $98.04. So let's suppose that, to take again our first observation about present value and relationships, let's suppose that we have an interest rate still of 2%, but you're promised the $100 5 years from now. So what's the present value? Well, the present value is numerically $100 divided by 1 plus 0.02, so 1.02 raised to the 5th power. And if I did this correctly, the number that you would get here is $90.57. So what is this saying? This is saying, and you can check the math, that if you had $90.57 today, it would grow to be $100 in 5 years. Similarly, if you had $98.04 today and the interest rate is 2%, and it would grow to be $100 1 year from now. So why is it that a certain amount of money to be received farther into the future is worth less to you today? Well, one reason why is you just have to wait longer to enjoy the benefits of that. And then importantly, as we were describing before, if you had the funds today, like in other words, the $100 today, it would have grown, and you saved it. say at 2%, it would have grown in value. Of course, this is the idea of compounding. And it would have grown to an even larger amount after 5 years, compared, of course, compared to just one. So the promise to receive this $100 5 years from now is worth less to you when the interest rate is the same than the promise to receive $100 just 1 year from now, because you can use those funds in whatever way gives you benefits sooner. So one way in which you could have used those funds is to save it and have earned interest. So our second comment here is that for a given amount to be received T periods into the future, the higher is the interest rate, the smaller is its present value. This relationship is going to be the one that we exploit when we talk about or when we ultimately derive the investment demand schedule. So again, let's think about this one. So for our second comment, we have that the higher the interest rate, the smaller the present value of an amount to be received, say T years from now. And again, it turns on this issue of compounding. So again, let's do an example, and then we'll try to provide some logic for it. So let's suppose that you are promised $100 in 3 years. If the interest rate is 2%, then we can figure out the present value of that. It's $100 divided by 1.02 raised to the third power. And that would be $94.23 again, assuming I punch numbers in into the bank, into my calculator correctly. If thinking about interest rates and talking about banks, if the interest rate was instead 7%, we would see that this is $100 divided by 1.07 raised to the third power, and that gives us numerically $81.63. So probably obviously, because the interest rate is what's included in the denominator, if the denominator gets bigger in a fraction, then the whole fraction becomes smaller. So from a mathematical point of view, we should expect that our statement is true. But the other way to think about this, again, is in terms of interest income that's foregone. So because of compounding, a certain amount of money is going to grow more, of course, when the interest rate is higher over a given time period. So therefore, the promise to receive something in the future is going to be worth less to you the higher is the interest rate. So if we flip this present value calculation on its head, we could say if we had $100 now and the interest rate is 2%, then in 3 years we'd have $100 times 1.02 raised to the third power, and that's going to be $106.12. if the interest rate is 7%, then in those same 3 years, getting $100 or saving $100 would yield $122.50. And so again, we have this observation that because you are giving up the opportunity to have the benefits of those funds when they are to be received in the future, and because the benefits of getting those funds in the future are going to be higher, the higher the interest rate is, we see this relationship that the higher is the interest rate, the smaller is the present value of a certain amount of money to be received in the future. And again, this will be something that we turn to when we develop the investment demand schedule. For now, what I want to do is direct your attention to the first of our participation questions. So what I want to do at this point is to uh, talk for just a minute about interest rates. So if you recall from our earlier discussion, we said there's a difference between real and nominal interest rates, and indeed we even said there's a difference between interest real and the realized real interest rate and the one that you are using in your decisions about borrowing and lending. So we can make the observation that these math problems for compounding and discounting we can use either the nominal interest rate or the real interest rate and come up with a similar sort of qualitative story. The only thing is that you would have to be consistent. So if you're evaluating the nominal value of your funds, then you would be using a nominal interest rate. If you're evaluating the real value of funds, then you would use a real interest rate. For what we're going to be doing as the semester proceeds, we're going to focus on real interest rates in our analysis. And so from this point forward, any kind of calculation that we're going to be doing, if it's not explicitly said that these are real interest rates, you should assume that they are. But I'll try to be explicit in things that I do and say going forward. So let's consider a specific example of an investment project. So we have Martha. Martha is a piano instructor, and she's thinking about whether to buy a new piano. So you can think about a piano as sort of being a machine that generates income in the sense that for Martha and the music academy, because as you have pianos, then students can come in and take lessons, they can be rented out, and so forth. And so the cost of the piano is around $148,000. So we'll say is specifically $148,000. Now, the piano doesn't just sort of sit around in its pristine state for time immemorial. It will depreciate from 1 year to the next, as would any kind of physical capital. So, as time goes on, it might require more in the way of tuning or basic maintenance. And this is certainly going to be true for machinery. I'm a little bit less well versed in pianos, but here we go. So we'll suppose that this piano is going to depreciate at about 5% per year. We'll also suppose that this $148,000 is could be used to purchase a piano, but the next best thing that could be done is that the academy could save it for another project that it might consider. And so if it saves it, it has an investment fund, a savings, glorified savings account, where it could earn a real return of 10% per year. So again, we'll get rid of the casualness of this. So it is 10% that is returned, 5% is the depreciation. And we'll suppose that by having this piano, being able to offer lessons and rent it out, will generate for the Piano Academy $30,000 per year, and that amount is going to keep up with inflation. So this amount is in real terms. So should Martha acquire the piano? Well, what I want to do is unpack this a little bit. So let's consider if I can advance this. I have just made smaller with some bolding the statement that was on the previous slide. So, what are the things that we need to do to read these kinds of problems? So, there is an upfront cost that's incurred today, and for the piano, that's $148,000. We're going to assume that Martha earns $30,000 in real terms for each year that she owns this piano, and in our example, she's going to keep this piano for an infinitely long time period. So, is that fully realistic? No, but it gets us to some shortcuts in terms of math for evaluating this investment opportunity. We'll also suppose that as the piano ages, so in other words, after the first year that it's in place, it won't be quite as productive due to depreciation. So we're assuming that this rate of depreciation is constant, meaning it doesn't change, and it is 5% per year. And this then also, in characteristic of all the kinds of problems that we're going to be doing of this sort, is going to be the only reason for a decline in Martha's real revenues. So she would get, if there were no depreciation, in other words, she would get $30,000 year after year after year after year in real terms from this piano, but the quality of the piano erodes, and so she's going to get a little bit less. And again, we are supposing that the very next best thing that Martha can do with her $148,000 is to save it in an investment fund. So the foregone interest is what you would think of as the opportunity cost of using the funds to buy the piano. And so therefore, the 10% interest rate is the interest rate that should be used in these present value calculations. Because again, if she had $148,000, compounding would tell us that it would grow at 10% per year. So what I want to do is think about this, and I'm going to be, my characteristic fashion, a little bit tedious with this. This is similar to an example that's in the textbook that deals with wind turbines. So I just wanted to give you a different set of numbers to look at so that you had more to practice with. But remember that we have the depreciation rate is 0.05 or 5%. And the real interest rate is 10%, which, so 10% is the real interest rate. And so in our calculations here, we're going to have R is equal to 0.10. So what happens? So I have the first 5 years here, and I'll go through these calculations somewhat tediously. And you could do more years, or you could put this as the authors advocate into a spreadsheet and play around with some numbers if you wanted to. But what I have done is broken this apart into 3 columns. So the first column is just saying again, unadjusted for depreciation, this is in real terms, so inflation adjusted terms. The Piano Academy is going to get $30,000 year after year after year. But of course, this piano is going to depreciate by 5% each year. And as a result of that, then the revenues that the Piano Academy is going to get will fall by that depreciated amount. So in considering the revenue that would accrue to the Piano Academy in year 2, we are saying that depreciation sets in after year 1. And so we would be subtracting the, I'm just going to write 30K, $30,000 times 0.05. And the number that we would come up with here is 28,500 as the year 2 revenues. And again, what is this? This is the $30,000, the 30K, times 1 minus the depreciation rate. In year 3, further depreciation has occurred, so we're going to subtract 28,500 times 0.05, and the number that you would come up with here is that the revenues would be 27,075. And if we think about what this is the revenues that we had in year 2 minus this depreciation. So this is going to be 30K times 1 minus the rate of depreciation squared. And if we did this 2 more times, that's all, we would subtract for year 4 the depreciation, which would be 27,075 times 0.05, and we would get as the revenues 25,721. And what is this? This is $30,000 times 1 minus the depreciation rate, now cubed. And finally, we have as our number here $24,435. And I'll leave it to you to confirm that you could arrive at that by taking the $30,000 times 1 minus the depreciation rate to the 4th power. Now, you're not going to have to complete tables like this, certainly on an individual quiz. I don't know whether I'd be mean enough to make you do it on a team quiz, probably not. But the reason that I'm going through this is for those of you who are curious about the mathematics. And so I'll point you to that in of a little trick that we're going to turn to by the time we get to the next slide. So what is the present value of having this piano? Well, it would be the present value of the revenues that the Academy would get in year 1, plus the present value of the revenues that the Academy would get in year 2, in year 3, and so forth. And so we would note that if we were going to figure out what is the present value of getting $30,000 in 1 year from now, well, that would be, oh goodness, that would be $30,000 divided by 1 plus 0.10 raised to the 1st power. So again, the present value is the future value divided by, in this case, 1 plus r to the teeth power. So this amount would be $27,000, $27,272.73. Similarly, what is the value today of getting $28,500 2 years from now? Well, again, you could figure this out. This would be 28,500 divided by 1.10 squared. And if you do that math problem, you're going to come up with $23,553 and and 72 cents. Sorry. And similarly, we could go down this. This would be the number that we would be looking for is $27,075 divided by 1.10 to the 3rd power, because we're going to get that amount in 3 years from now. And so that number would be 20,000, again, all conditional on me typing numbers into a calculator correctly, but say 20,341.85, and then I'll just fill in these other 2 numbers so that you can check that you're doing your math properly. So this number you should come up with as 17,567.96, and in year 5, you would get $24,435. So what is today's value of the promise of getting $24,435 in 5 years? That should be 15,172.33. So $15,172.33. And this could go on and on and on. So these ellipses here are and so on, and etc. And so you could carry this out farther if you wanted to. What I am asserting for you is that the present value of buying this piano will tally to $200, or excuse, $200,000. So, what is in this column? So let me, again, just for sake of the people who are interested in the mathematics here, if we took this $27,272.73, what is that? That is the present value of, oh, I don't want to do that one actually. Sorry, let me do the next one. So the $23,553.72. What is that? That is the present value of getting $30,000 minus depreciation in 2 years from now. Okay, and so the pattern that you would see would mimic this sort of a calculation. So for those of you, again, who are interested in the mathematics behind this, I'll alert you to where you might look. But what I'm saying is if you add, so I am asserting that if you add 27,272.73 plus 23,553.72 plus 20,341.85 and so forth, you would get $200,000 as today's value of having this piano in place in perpetuity when the interest rate is 10% and the depreciation rate is 5%. Now, that's a lot of work, and we would literally be here forever if we carried this out to infinity time periods from now. So there's a shortcut that is handy to put into place, and the shortcut works because of the nature of the problem that we have. So the specific things that are key to this problem that will always be key to these sorts of problems in Econ 1021 is that we have a constant real amount of revenue which is only declining because at a constant rate. So the $30,000 was only declining because of depreciation, and depreciation itself is fixed. And so in that particular case, the shortcut way of figuring out the present value of a stream of returns is to use the valuation formula. And so the valuation formula tells us that the present value of the stream of payments, so in other words, the 27,272 plus the 23,553 plus, as we were doing in the previous column, is going to be equal to the revenue that would be received in the next year divided by the interest rate plus the depreciation rate. Now, what's the math? If you're interested, there's a verbal explanation of it on page 352. And there is, you'll see in our presentation here, we're going to hop from slide 13 to slide 15. Slide 14 takes you through the math. If you are interested and sort of want to nerd out on it, I think it's kind of cool, then take a look at it. I want to emphasize as loudly as I can, although I'm sure we'll have lots of Piazza questions, you are not responsible for the derivation of this shortcut. You just need to be able to do it. So, in other words, all of these problems are going to center on here's next year's revenue, here's the interest rate, here's the depreciation rate, what's the present value of the stream of payments. So, for example, we can then use that valuation formula, that shortcut, to develop what the authors of the textbook refer to as the rational rule for investors. So again, a rational rule is always a comparison of benefits and costs. So in this case, for investors means that they're looking at the benefits of having this project in place or undertaking investment and comparing it to the cost. So what are the benefits? The benefits are the present value of the future stream of returns. And the costs, of course, are the costs that get incurred upfront, typically upfront and today. So the rational rule for investors is to say yes when the benefit, so this is the benefit of undertaking the investment project, is greater than or equal to the cost. So in this particular case, you would undertake this project if the present value of the stream of returns exceeds the upfront cost. So in our example, you would say that the stream or excuse me, next year's revenue, so the year one revenue is this amount, $30,000. So this is the year one revenue. There's no depreciation yet because the piano is just put into service. And in our example, of course, the interest rate is 10% and the depreciation rate is 5%. And if we sum those, we get 0.15 in the denominator, do the division, and we come up with $200,000. So the present value of the expected future revenue stream exceeds the upfront cost of the piano. So Martha should say, yes, indeed, I totally want to do this. Now, what can we do to make this a little bit more relevant to our broader macroeconomic questions? Well, first of all, this framework that Martha used is a framework that you can apply to any kind of, investment decision, using the word colloquially, that you would face, and is certainly the manner in which firms are evaluating the variety of projects that they might undertake. So, what kind of machine should they buy if they knew that they wanted to expand their productive capacity, or should they build a new factory, and so forth. Those are all investment decisions. For you, should you buy a house? Down the road, that's an investment decision, and so you can use these kind of tools in that manner. So the key thing here is that the real interest rate, of course, is going to be playing a central role in investment decisions. We saw it literally in the denominator of that valuation formula. And our thing that I want to investigate at this point is this relationship between the real interest rate and the quantity of investment that is undertaken. So specifically, so this is our key idea, and this is what we're going to devote some time to right now. We saw that Martha would buy the piano when the real interest rate was 10% because the present value of the future returns exceeded her upfront cost. Suppose it's the case that Martha's Piano Academy's investment fund, rather than a 10% real return, had a whopping 18% real return. So these numbers have no bearing in current reality, but serve the purpose for what we're going to do. In this particular case, we could figure out again, what is this calculation? We're getting the present value. This is the present value of the future stream of returns. That's what this is telling us. So the depreciation rate isn't changing by assumption in our story here, but we'll say the real interest rate goes from 10% to 18%. What does that result in? Well, that results in a decline in the present value of having this piano in place, and a decline so much so that the present value of having the present value of the returns associated with having the piano is less than its cost. So Martha should say no to this piano purchase. So in this particular case, an increase in the real interest rate reduced investment expenditures from 148,000, the price of the piano, to zero. So that's pretty extreme, but Martha was in an all or nothing situation. If we take all of the Marthas in the economy, all across the economy, there are millions of economic agents that are evaluating potential investment projects. And if we want to take our example of an interest rate that's rising from 10% to 18%, there might be some projects that are still profitable when real returns are 18%. But what we know for sure is that there are some, like Martha's, that are not. And so what we observe is that when the interest rate is rising, so as the interest rate goes up, then there is a decrease in the quantity of investment undertaken, both at an individual level, like for Martha, but also at a macroeconomic level. So with this, we're going to pause for another participation question. Okay, so the big takeaway here, again, there is an inverse relationship between the real interest rate, between the real interest rate and the quantity of investment spending. So why is that? Again, it is because when interest rates rise, there are fewer investment opportunities or projects that will satisfy that rational rule for investors. So again, what is the rational rule for investors? We're asking, is it the case that next year's return divided by R plus D, is that greater than or equal to the cost today? So the higher, right? So the higher is, if we increase R, then for reasons that we've already talked about, we decrease the next year's return divided by R plus D. So mathematically we can see that, but we also talked about logically why that's true. So there are fewer projects that will pass the net present value, will satisfy this rational rule for investors. And so I'm going to have another illustration of this, is the week 1 homework assignment that, because it's sort of late that I'm going to be posting it, I'll probably push it to a due date of Sunday rather than Friday, but you will see that. And I'll try and walk you through, as I said, just another interpretation of this. Now, this inverse relationship between the real interest rate and the quantity of investment spending is essentially describing a demand curve. A demand curve for what? Well, a demand curve for investment. So what we're going to do down the road, namely in the part 3 notes, is we're going to put here the quantity of loanable funds. And what are loanable funds? It's the level of savings in the macroeconomy and the level of investment that's undertaken in the macroeconomy. And we're going to put on the vertical axis the real interest rate, and we're going to draw a downward sloping relationship here. And we'll call this the demand for loanable funds, but what this is a reflection of is investment expenditures. So in other words, again, we have this observation that if the interest rate goes, say, from R0 to R1, then the quantity of investment demanded is going to fall from I0 to I1. That's what we've just talked about. Now, this is conditional, of course, on all other things held fixed. And that's what we're going to turn to next. But before that, we have our final participation question. So as I said, let's see if I can make the eraser thing come down. As I said, we have discussed now or traced out now an investment demand schedule. And we based that observation on the rational rules. So again, I'm going to run into problems here. Goodness. So sorry. I'm just running into difficulties with this.